Assalamualaikum dear students. We saw in our previous lecture, we were studying negative feedback, effect of negative feedback. Okay. So we took an example of non-inverting amplifier where we using operational amplifier, where we saw that we have a feedback path. Feedback resistor was connected through a feedback path, which was responsible for negative feedback in the circuit. Okay. So this is an example of non-inverting amplifier, and we saw in this amplifier in this circuit, once we increase the output because of negative feedback, there is a mechanism that it will finally cause decrease in output. It will compensate the increase in output voltage will be decreased because of the negative feedback. So there will be no change in the output because of the negative feedback that is connected in the circuit. Okay, so we can say that due to negative feedback, present in the amplifier, due to negative feedback, Vd becomes small. Okay, Vd becomes small because when negative feedback is connected, we know that differential input, the difference between two inputs, it becomes very small. Okay, Vd becomes very small. So Vd becomes very small. It is nearly equal to 0. We can say then Vd is nearly equal to 0. Okay, Vd is nearly equal to 0, or it is approximately equal to 0. When we say Vd differential input is nearly equal to 0, because we know what is Vd. Vd is basically difference of these two inputs. It is the differential input of the operational amplifier. So Vd is nothing but it is equal to Vi minus Va, input voltage minus node A voltage. Okay, so differential voltage in this circuit, it is equal to Vd is equal to Vi minus Va, V non-inverting minus V inverting, or V1 minus V2. Okay, so if we substitute Vd here, so we can say Vd is nearly equal to 0. That means Vi input voltage minus Va is nearly equal to 0. And we can finally say that Vi is nearly equal to Va. Okay. Now we also know what is V input. V input is nothing but uh, it is the output. Sorry, Va. Okay, Va we know. Va, we have already known, we have calculated Va from equation 1. Va is basically output of the voltage divider network. Va is output of voltage divider network, and it is equal to V naught into R divided by R plus F, divided by R plus F. Okay, divided by R plus F. So we can say then V input, since V input is equal to Va, we can say then, since Va, okay, Va, we know that it is equal to V output into R divided by R plus Rf, then we can say that this V input, it is equal to V naught into R divided by R plus Rf. Okay, Rf. If we calculate, rearrange this equation, if we calculate V output out of this equation, then we can say that V output, on rearranging this equation, V output can be written as V input into R plus Rf divided by R plus Rf divided by R. And we can further write down V output, it is equal to 1 plus Rf divided by R into V input. This is the final equation of this non-inverting amplifier. Okay, this is the final equation of this circuit that we have drawn here, that we are discussing. So the final output of this circuit, mathematically, the expression of the V output, the output can be calculated by equation 3. That is, V output is equal to 1 plus Rf divided by R into V input. Okay. So from equation 3, we can see that V output is directly proportional to V input. V output is directly proportional to V input. Or V output is some positive constant times V input. Positive constant times V input. Therefore, we say that V output and V input are in phase. V output and V input are in phase. That is, phase difference between input and output is zero. Phase difference between input and output is zero. Okay. It means that we have a same circuit here. I have drawn the circuit here also. It means that if we have an input like this, you have a positive half first and negative half first, negative half after that. If you have a sinusoidal input with a positive half first, then a negative half cycle after that, then the output will be amplified because it is amplifier, but there will be no phase difference. Phase shift between input and output will be zero. Okay, phase shift between input and output will be zero. Phase shift between input and output will be zero. So that is what I'm saying, that the phase shift between input and output is equal to zero. Okay. Now, suppose for a general amplifier, we know if we have an amplifier like this, you have an amplifier, there is some input and there is some output. We know for any amplifier, V output is equal to gain times V input. V output is equal to gain times V input. Now see, say for example, this is equation 4 now. Okay, suppose this is equation 4. If we compare equation 4 and equation 3, we will be able to find out that the gain of the non-inverting amplifier, it is equal to 1 plus Rf by R. Okay, so this is the gain, this much is the gain, whatever is present in equation 3 and that I have highlighted here, that is the gain. So in this amplifier, okay, non-inverting amplifier, in this non-inverting amplifier, the gain is equal to 1 plus Rf by R, 1 plus Rf by R. So it is equal to 1 plus Rf by R. So gain, it is equal to 1 plus Rf by R. Okay. So I have taken the same circuit here, non-inverting amplifier. I have drawn it, I have redrawn the circuit here. Okay. I can now say V output, the output expression, mathematical expression for this amplifier is V output can be calculated by 1 plus Rf by R into V input. Okay. And here 1 plus Rf by R is nothing but it is gain. Since this circuit has a closed loop, it has a negative feedback. There is a closed loop, okay, like this. You have a closed loop here. So since you have a closed loop here, there is a feedback here. The gain that is present in the circuit is known as closed loop gain. It is known as closed loop gain, or it is also it is represented by ACL. ACL would mean closed loop gain. Closed loop gain. Okay. So it is closed loop gain. It is closed loop gain. Therefore, we can say then, hello. Therefore, we can say then amplifier. This amplifier is having a gain equal to 1 plus Rf by R. We can say that okay. So therefore, Therefore, uh, I can say then, hello, hello, hello. Uh, so we have redrawn this amplifier here. Okay, I have redrawn this amplifier here. This is a non-inverting amplifier. I can say that the general expression for this non-inverting amplifier is V output is equal to 1 plus Rf by R. V output is equal to 1 plus Rf by R into V input. What is 1 plus Rf by R? 1 plus Rf by R is the gain. Okay, it is the gain of the circuit, because general expression for an amplifier is V output is equal to gain times V input. So we have V output 1 plus Rf by R times V input. So 1 plus Rf by R is gain. Since this circuit, it has a closed loop present, there is a closed loop in the circuit. Okay, negative feedback is present. Therefore, the gain is known as closed loop gain, and it is denoted by ACL. It is known as closed loop gain. So it is denoted by ACL. ACL is the closed loop gain of the circuit. Okay. So we can then summarize the amplifier. This amplifier, non-inverting amplifier, its gain is equal to 1 plus Rf by R, which is equal to ACL, which is equal to closed loop gain. It is not its open loop gain, because there is a feedback now. It is not open loop configuration now. It is a negative feedback configuration. Therefore, its gain will be equal to closed loop gain. And its gain is, how much is that equal to? Mathematically, it is equal to 1 plus Rf by R. Now, the good thing about this circuit is that we can adjust Rf and R. We can adjust Rf and R so that we can tune, we can adjust, that will help us in adjusting the value of ACL also. It will help us in adjusting the value of closed loop gain. So the closed loop gain of this circuit, it is quite flexible. The closed loop gain of this circuit, it is quite flexible, and we can adjust it, we can tune it with the help of RF and R, with the help of feedback resistor and R that is connected in the circuit. Okay, that is one of the biggest advantages of the circuit. And ACL is nothing but the closed loop gain. Uh, Now, output resistance of the circuit, since the circuit is having some negative feedback, it is having a negative feedback present in it. Therefore, output resistance is denoted, or it is written by ROF. ROF would mean output resistance with feedback. So output resistance with feedback will be very small. Okay, it is further small. Generally, the output resistance of operational amplifier is small, but once we connect negative feedback, the output resistance becomes further smaller. So it is nearly equal to zero. It is nearly equal to zero. Okay, but it is not exactly equal to zero, but it is very small, very small. And bandwidth is the range of frequencies that this non-inverting amplifier is capable of amplifying, that it can amplify. Okay, bandwidth of this circuit is equal to UGB is unity gain bandwidth, unity UGB by A closed loop. So bandwidth, how much is the bandwidth of the circuit? Bandwidth is equal to unity gain bandwidth divided by closed loop gain, divided by closed loop gain, whereas UGB is unity gain bandwidth. And unity gain bandwidth is generally calculated by A open loop into omega open loop. Omega open loop is frequency in radians. Okay, so I'll explain unity gain bandwidth in coming lectures also. So that was all about non-inverting amplifier. Please remember that non-inverting amplifier has a gain equal to 1 plus Rf by R. It has gain equal to 1 plus Rf by R. Okay, now the second circuit that we would like to discuss here is inverting amplifier. Inverting amplifier. Inverting amplifier. In inverting amplifier, the circuit looks quite similar to non-inverting amplifier. If we compare non-inverting amplifier and inverting amplifier, you will see that you have an operational amplifier here. I would like to mention that this is an inverting amplifier, but using operational amplifier. okay, using operational amplifier. If we compare, if we compare these two circuits, if we compare these two circuits, okay, we will see that we have operational amplifier here, we have operational amplifier here, okay, in non-inverting amplifier. And we also have a feedback resistor that is somewhere here. We also have a feedback resistor here also, okay. So it is quite similar. We also have output, we also have output here. So the circuits are quite similar. Then you have input resistance, that is somewhere here. Then you have input resistance here, okay. The only difference between input non-inverting amplifier and inverting amplifier is that in non-inverting amplifier, please remember, in non-inverting amplifier, the input Vi is applied to non-inverting terminal, okay. The input is applied to non-inverting terminal. While as in inverting amplifier, the input is applied at inverting terminal, okay. The input is applied at inverting terminal. The input is applied at inverting terminal. The input is applied at inverting terminal. So we have here input which is applied at inverting terminal. In inverting amplifier, the input is applied at inverting terminal. So we should remember in inverting amplifier, first of all, the phase difference between input and output, it is equal to 180 degree. That is, the phase shift between input and output signal is 180 degree. It means that if you apply a V input signal, a sinusoidal input signal which has a positive half first followed by a negative half cycle, then your output will be 180 degree out of phase. That means in your output you will obtain first negative half cycle, then you will obtain a positive half cycle. That is what is meant by a phase shift of 180 degree between input and output signal. Okay. The second point we have to remember that in this circuit, inverting amplifier, RF and R, RF and R, which are the feedback resistors and the input resistance. These resistors, they create the negative feedback in the circuit. Okay, they create a negative feedback in the circuit. And the type of feedback here, it is voltage shunt feedback. I have not explained the types of feedback. Maybe in coming lectures I will explain them. So due to negative feedback, since we have a negative feedback in inverting amplifier now, due to negative feedback, we know there will be a virtual short circuit. Okay, virtual short circuit will be present between input nodes. So due to negative feedback, there will be virtual short circuit. If there is virtual short circuit, we know differential input will be very small. Differential input will be very small. Or I can say, if there is a virtual short circuit and non-inverting node is grounded, then the same ground will reach to VA. The same ground will reach to VA. Why? Because here VD is nearly zero. VD is nearly zero. That means V positive, when VD is nearly zero, it means that V positive is equal to V negative. Okay, V positive is equal to V negative. So differential input is nearly zero, therefore VA will be equal to zero. VA will be equal to zero. Let me remove some steps. I'll go for. Okay. So please remember, if differential input is zero, therefore VA will be also zero. Why? Because there will be a virtual ground approximation. I have already discussed virtual ground and virtual short circuit in my previous lecture. Virtual ground comes because of virtual short circuit. Since there is a virtual short circuit in the circuit, and if we apply ground to any input terminal, whether inverting and non-inverting, this ground will reach virtually to other terminal also. So VA will be zero. Okay. Now, if we apply KCL, at node A, what is node A? Node A is somewhere here. If we apply KCL at node A, we will be able to find out that there are two currents, I1 and I2. There is no current. Please remember, there is no current going or moving from node A towards the operational amplifier. Since operational amplifier has a very high input resistance, there will be no input current going to op amp. So only two currents will be at the node I1 and I2. I1 and I2. Okay. So once we apply KCL, I1 plus I2 will be equal to 0. I1 plus I2 will be equal to 0. What is I1 equal to? I1 is equal to VI minus VA divided by R. Okay, VI minus VA divided by R. So it is difference in voltage divided by resistance of the branch. That is the current in the branch. So I1 is equal to VI minus VA divided by R. Similarly, what is the current in the branch, which is the feedback branch, feedback path, where RF is present? So it is equal to V output minus VA divided by RF. V output, difference in voltage, V output minus VA divided by RF. So difference in the voltage divided by the resistance of the path. That will be equal to 0. Okay. Now, since we know VA is 0, VA, we have already seen that it is equal to 0. Okay. So if we substitute VA equal to 0 in this equation, then we will be able to find that we will be left with VI by R plus V output by RF is equal to 0. Once we rearrange them, okay, we rearrange these steps, these terms, and we will be able to find out the output voltage expression for the circuit. Which circuit? Inverting amplifier. Okay, inverting amplifier. The output expression, output voltage expression for the circuit. So what is the output voltage expression? Equal to V output is equal to minus RF by R into V input. Okay, V output is equal to minus RF by R into V input. Now, say for example, this is equation 4. We know general equation for an amplifier, it is equal to V output is equal to gain times V input. We say for example, that is equation 5. If we compare 4 and 5, we will be able to find the gain of this circuit is equal to minus times RF by R. Minus times RF by R. Okay, gain is equal to minus times RF by R. And since you have a negative feedback here in inverting amplifier also, so the gain will be closed loop gain. The gain will be closed loop gain. So if we try to compare it with the previous circuit with non-inverting amplifier, we'll be able to find here you had, we have here V output is equal to negative constant times input. Whereas in our previous circuit in non-inverting amplifier, the case was V output was positive constant times input. Positive constant times input. That is the difference here. Now see, the negative term here would mean phase shift of 180 degree. Negative term here would mean a phase shift of 180 degree. Negative term would mean here a phase shift of 180 degree. 180 degree. Negative phase shift of negative term would mean 180 degree phase shift. Okay, 180 degree phase shift. This means if you will give an input signal which has a positive half first, then negative half after that, your output will be like this: negative half cycle first and positive half cycle after that. Okay, after that. So this was all about inverting amplifier. And please remember that there is a difference. There is a difference in gain. In non-inverting amplifier, the gain was 1 plus RF by R. Whereas in inverting amplifier, the gain is equal to minus RF by R. It is equal to minus RF by R. Okay, so that is the difference here, gain. But please note that in both these circuits, the gain can be adjusted. We can adjust the gain. Here also, we can adjust the gain by changing the values of RF and R. If we change the values of RF and R, we can see that we can adjust the gain also. Okay. So we have so far now we have taken two examples of negative feedback. One is a non-inverting amplifier that actually started from here, non-inverting amplifier. Then using operational amplifier, then we took uh, inverting amplifier using operational amplifier. Okay, inverting amplifier using operational amplifier. The third example would be voltage follower circuit. Voltage follower circuit using op amp, using operational amplifier. Okay. Now see the circuit of a voltage follower circuit. It is given here. There is a feedback, negative feedback, of course, because it is an example of negative feedback, but there is no feedback resistance present. Please note that there is no feedback resistance present. Okay, it is a short. There is a short between V output and V input, inverting input, and the input signal is given. The input signal is given to the input signal is given to V non-inverting terminal, non-inverting terminal. Okay, so this is the circuit. Now see, so output node and inverting input is short circuited physically. They are short circuited physically, and due to physical short circuit, in this circuit, you can see that VA is equal to V output. Okay, whatever is voltage at node A, that is the voltage present at output voltage. Okay, so VA is equal to VA. VA is equal to V output. That is the first thing. Second thing, since there is a virtual, this was a physical short approximation. Since there is a negative feedback, there is a virtual short circuit also. Okay, since there is a negative feedback in the circuit, because we know in negative feedback, one of the approximation in all the circuits, we assume that there is a virtual short circuit present. Okay, there is a virtual short circuit present. So since there is a virtual short circuit also, then VA is equal to VI. That means these two terminals, they are shorted together. Okay, they are shorted together. So virtual short circuit would mean inverting and non-inverting terminals are short. They are at same potential. They are at same potential. Physically, they do not have a short, but it is a virtual short. Okay, it is a virtual short. So due to virtual short circuit, VA that is here. What is VA? VA is something this. So this is V of A. VA is equal to VI. VA is equal to VI. Due to virtual short circuit, VA is equal to VI. So say for example, this is equation 2. Now from equation 1 and from equation 2, we can see that V output is equal to V input. V output is equal to V input. So from this expression, we can see that output voltage is equal to input voltage, or we can say output voltage follows input voltage. Output voltage follows input voltage. That is why this circuit is known as voltage follower circuit. Voltage follower circuit. Okay. Now, if we try to find out the closed loop gain of the circuit, a closed loop gain will be equal to, gain is equal to output by input. So what is the output of the circuit? It is equal to V output by V input. Since V output by V input, they are same, then the gain will be equal to 1. Okay. So please remember, this circuit is very special circuit. It is a special amplifier which has closed loop gain equal to unity. That is why this is known as unity gain circuit or unity gain follower circuit, voltage follower circuit. So it has closed loop gain equal to unity. Therefore, it is also called as non-inverting amplifier with unity gain. It is a non-inverting amplifier. Why? Because input is applied at non-inverting terminal. Input is applied at non-inverting terminal. Okay. So it is called as, therefore this circuit is called as non-inverting amplifier with unity gain. Non-inverting amplifier with unity gain. And here the input resistance with feedback will be very, very large. Normally, operational amplifier has very high input resistance, but because of negative feedback, input resistance is, nearly infinite. It is very large, and therefore input current, what is the current that will flow into operational amplifier? It will be nearly equal to 0. So input current will be nearly equal to 0, and output resistance with feedback will be very, very small. Like in previous circuit, we said bandwidth, the range of frequencies that it can amplify or it can pass, it will be equal to unity gain bandwidth divided by closed loop gain. But see, closed loop gain here in this circuit, it is equal to unity. Okay, closed loop gain in this circuit, it is equal to unity. Therefore, the bandwidth of this circuit is equal to unity gain bandwidth. Sometimes it is also known as small signal bandwidth. Okay, so bandwidth is directly equal to unity gain bandwidth. Now, this circuit is very special. In a way, it has many applications. I'll stop after applications. It has a very popular application that it is used as a voltage buffer for impedance matching. Voltage buffer. Now, see, please remember that since input voltage is equal to output voltage, a buffer is a circuit that stores temporary signal and then passes it on to the next stage. So it seems that it temporarily stores the voltage for some time because V output is equal to V input. There is no change in the input. Whatever is input, same will be obtained from the output. So it temporarily stores the voltage and then forwards it to the next stage. Now, see, its input impedance or resistance is one value, and its output resistance with feedback, it has a different value. So it can match two different impedances. It can match two different stages with different impedances. That is, it can match a stage one. Say, for example, this is voltage follower circuit. Then this is stage two. Okay, and you have stage one here. So its impedance is omega, and this is k omega, for example. It is very high and it is very low, for example. Okay, so it can match these two stages also. And matching of impedance is very important as far as maximum power transfer theorem. Okay, in order to have maximum power transfer, we know that impedance matching between stages is very important. Okay, it is also used in sample and hold circuits. Sample and hold circuits are circuits which are used in data converters in order to convert one signal or analyze one signal. We sample an analog signal if we want to convert it to digital code. So there are many applications for sample and hold circuits, but this is used there also. One of the biggest and most popular applications for voltage follower circuits is they find a wide application in instrumentation amplifiers. We'll be studying instrumentation amplifiers in coming lectures. I'll discuss it there also. So they are also used in instrumentation amplifiers, special amplifiers, uh, which are used in sensors. Okay, they are used in sensors. They are used in picking up very weak signals and then uh, amplify it to a level where it is appropriate for analysis. Generally, um, these instrumentation amplifiers, you'll find them. A wide variety of instrumentation amplifiers is found in sensors or even in medical biotechnologies, medical instrumentation technologies. So they are generally found in instruments, measuring instruments, or even in sensors, these instrumentation amplifiers. Uh, Fourth application is they are used in first order Butterworth filters. Filters we'll be studying in our coming lectures. I'll discuss there what is a Butterworth filter. But we should remember that a voltage follower circuit, it is also used in first order Butterworth filter. So I would conclude this lecture by saying that we have discussed three different applications of negative feedback. Okay. One is non-inverting amplifier, operational amplifier as non-inverting amplifier. That is this one. Then we studied also operational amplifier as inverting amplifier. Then we also studied operational amplifier as voltage follower circuit. Okay, voltage follower circuit.